Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about wet scrubber. First, let us understand what a wet scrubber is and how does it function. And wet scrubber is a device where high turbulent mixing is created between a gas phase and a liquid phase, where the gas phase contains particulate matter suspended in it. And as the mixing occurs, the particulate matter in the gas phase tends to get arrested by the liquid phase, thereby the gas phase gets cleaned. Usually there are two types of scrubbers that Aspen Plus can handle. One is Venturi type scrubber, another is the spray tower type scrubber. Let us understand how they work. This is a schematic diagram of a Venturi scrubber. It has a converging section, a throat of Venturi, and a diverging section. It has three configurations. In all the configurations, the gas phase is fed from the top and liquid is fed either at the Venturi throat or somewhere over here. In all three cases, the gas phase, when it goes through the Venturi, in a converging section, its velocity increases manifold. And the liquid is also pushed in the Venturi section, thereby high turbulence is created between the gas phase and liquid phase, thereby the particulate matter gets arrested by the liquid phase. And as the particulate matter gets arrested in the liquid phase, and due to this Venturi section and high pressure, the liquid phase is sprayed over this region and it is transferred to another vessel where the slurry goes out like this, and the clean gas, its outlet is something like this. And obviously, if such a high velocity turbulence is created, some mist will also form in the vessel. So there will be a mist eliminator over here. So this mist eliminator will eliminate the mist. So here the gas outlet, it will contain only the gas phase, no liquid and no particulate matter. That is what expected in ideal case, but in real case, obviously some amount of liquid and some amount of particulate matter will still be there in the gas phase. So efficiency of a scrubber is defined as what is the fraction of particulate matter that has been arrested in the liquid phase, which were fed into the system. Okay. So if X amount of particulate matter has been fed through the gas phase and Y amount of particulate matter has been arrested in the liquid phase, obviously X would be greater than Y, then the fraction of Y by X will be equal to the efficiency of that particular scrubber. So this is about Venturi scrubber, and this is the schematic of a spray tower. As the name suggests, you can find that there is a spraying section over here through which the liquid is being sprayed and gas is fed from the bottom. So gas will travel like this and it will exit from this section. Here also there will be a mist eliminator, and this mist eliminator will eliminate the mist, whatever it has formed inside the vessel. So clean gas, that means the gas without any mist and without any particulate matter is expected to come out of the scrubber. And obviously efficiency will be defined as the ratio that I have mentioned a couple of minutes back. And this is the outlet for the slurry in the case of spray tower. Now let us go to the Aspen Plus window and learn it further. Wet scrubber is obtained over here. In the model palette, solid separator, you will find over here. So this is the V-scrub model block. So this is the block of scrubber. It has two mandatory inputs and two mandatory outputs. This is the input for feed, which will contain the gas phase where the particulate matter is suspended. And this is the liquid phase that will arrest the particulate matter. This is the outlet of gas, which is supposed to be the clean gas, and this is supposed to be the liquid. Let us rename them as feed. This is liquid. This is clean gas. And let us write it as liquid out. Okay. Now let us go to the block input and see what are the things that are needed. So in scrubber, in addition to Venturi scrubber and spray tower scrubber, we have the third option, solid separator. Now this solid separator has already been explained in the cyclone block. It works in the same manner. So if you choose the solid separator, it will ask for certain information like solid load of vapor outlet, vapor load of solid outlet, fraction of vapor to vapor outlet, any one of them, and fraction of solids to solid outlet or fraction of vapor to vapor outlet. So these two information will be asked, and also you will be asked about the classification characteristics like either particle size or particle settling velocity. You have to specify the separation sharpness and offset of fines. You already know what they are. And the outlet flash specification like what is the pressure or temperature change or duty. So if you provide all this information, it will do some calculation on the basis of algebraic manipulation and it will give you the final answer. Now the example has already been given in Cyclone, so you can check that block and you can learn it better. But the moment you choose this Venturi scrubber, there will be two modes, simulation and design. Okay? And there will be two calculation methods, Young and Calvert. So you can work either in simulation mode or in design mode, and you can use either Young calculation method or Calvert calculation method. You will learn these calculation methods better in the help file. So you go to specifying V-scrub. Here you will find the definition of separation efficiency for Venturi scrubber. This definition was discussed a few minutes back. It is the ratio of mass flow rate of the particles of outlet liquid stream by the mass flow rate of particles in the gas stream. And that can be calculated using these two, where eta I is the efficiency of size increment I and SI is the mass flow rate of the size increment I. For each and every size increment, we have to find out this particular eta I, which is a function of many things like this. One is xi, that is the particle size class I, rho solid J is the density of class J, mu gas is the dynamic viscosity of the gas phase, delta P is the pressure drop, F is the fitting parameter according to Calvert. That can be varied from 0.25 to 0.5. Now this Calvert method has been given in these two references and Young method is given in this reference. Now you can see these references. If you click over here, it will come. First 1, 2, 3 are the Calvert method and 11 is the Young method. You can refer these papers to learn it better. So you can see the efficiency is a function of delta P as well. All other things are set by the system properties, but delta P is not set. So either of them has to be specified. So if you specify the efficiency, then you can back calculate delta P, and if you specify the delta P, then you can calculate the efficiency. Now, how it is done? When you design something, you have to provide the separation efficiency and these two figures, volume ratio and droplet to gas velocity. So this can be understood better over here. See this equation. Beta is equal to droplet to gas velocity ratio. So you have to specify over here. So if you know this droplet to gas velocity ratio, you can calculate X. Okay, what is X? X is dimensionless throat calculated to satisfy this equation. So once you specify beta over here, X can be calculated. That X will be used over here. Rho L and rho G, they are the densities of liquid and gas. DD and CD, they are calculated from here. CD is the drag coefficient, which is dependent upon the Reynolds number, and the Reynolds number will be calculated by Aspen based on the geometry and fluid properties, its velocity and through which channel it is going. The Reynolds number will be calculated over there. And DD is the drop diameter, that is shorter mean drop diameter. To calculate that, you need all those information. And one of them is this QL by QG. And that is the volume ratio, liquid to gas volumetric flow rate ratio. And this ratio needs to be provided over here. That is the volumetric ratio. And all other things are known. You see, the VT is relative velocity of gas to liquid at the throat. Now, if you specify the throat over here, whether it is round shaped throat or annular gap or square or rectangular, and you can see all other information like rho G, rho L, sigma L, the surface tension, mu L, the viscosity of the liquid. These are all obtained from the Aspen property database, so you do not have to supply these values. Only this liquid to gas volumetric flow rate will be calculated by itself. Relative velocity will also be calculated by itself, and DD can be calculated. So LT is the throat length of the Venturi scrubber. So this thing will be calculated by Aspen. And this is the pressure drop, which is again, say for Young's model, pressure drop is a function of all these things. So this is the beta, right? Which you have already specified over here, the beta value. That is droplet to gas velocity ratio. QL by QG, VT, rho L, GC. GC is the conversion factor in Newton's law of motion. So it is 9.81, I believe. And rho L, VT square, all of them are known. So delta P will be calculated by this. So here you can see the efficiency and delta P, they are related. So in design mode, when you are specifying the separation efficiency, that means you are asking Aspen Plus to design the Venturi scrubber in such a way that the separation efficiency is exactly that much. So delta P will be calculated based on that. On the contrary, if you go to the simulation mode, then you have to specify either the throat geometry or you have to specify the gas velocity at the throat. If you specify the throat geometry, you have to tell whether the throat is round shaped or it is square shaped or it is annular gap or rectangular. If it is square shaped, obviously only throat width has to be given. It is just square. If it is rectangular, then the two sides are not same, so you have to give the throat width and height. If it is round shaped, then you have to give the throat diameter, and if it is annular, then you have to give two diameters, throat outer diameter and throat inner diameter. And if you want to use the design mode with culvert model, then in addition to the throat type and separation efficiency, you have to provide the throat outer by inner diameter ratio also. Or if it is a rectangular thing, then you have to give throat width by height ratio. If it is round or square, then you do not have to give those ratios, because for square case, this ratio will always be 1, and for round case, this is only one diameter, not inner and outer diameter. So it will be only one diameter. There is no question of ratio over there. And in the simulation case, again, for culvert method, if it is square, you have to give only throat width. If it is rectangular, then you have to give this throat width and throat height also. If you use Young method, then in addition to these data, you have to give the throat length as well. So throat length will not be calculated by the Aspen Plus, because you are specifying the throat geometry over here. So throat length also you have to provide. Or else you have to specify the gas velocity at the throat inlet. That will be used to calculate the pressure drop, and that pressure drop will be eventually used for calculating the separation efficiency. So just to recapitulate, for simulation method, you have to provide all the throat geometry, throat length, etc. and do the simulation. Whereas in design method, you specify your separation efficiency, and all of them will be calculated in such a way that it achieves that particular separation efficiency. So that is the difference. Now this is about the Venturi scrubber. The spray tower scrubber is similar. Only thing is that Young method is not useful for spray tower. You have to use only culvert method. Their separation efficiency has to be put in order to do it in design mode. Now, you can calculate the sorted diameter of the droplet. Then you have to provide this nozzle orifice diameter and nozzle spray angle, and also the number of nozzles. Nozzles, you remember, these are the nozzles. Like in the spray chamber, you remember there were some spray nozzles over here. So the diameter of the nozzle, the angle of the nozzle, and also the number of the nozzles. All these three things you have to specify. Or you have to specify the sorted diameter of the droplet. If you know the sorted diameter of droplet, you have to say that I want the sorted diameter of the droplet to be this. Then you also have an option to calculate the number of nozzles. And in that case also, you have to specify the orifice diameter and spray angle of the nozzle as well. Or if you give the relative gas velocity, then also based on the separation efficiency that you desire, your sorted diameter will be calculated. Now let us solve a problem to understand it better.